In this research paper titled, Enhancing the Geometric Problem-Solving Ability of Multimodal LLMs via Symbolic Neural Integration, a team of researchers from the University of Science and Technology of China and iFlyTech Research, including Yicheng Pan, Zhenrong Zhang, Pengfei Hu, Jifeng Ma, Jun Du, Jianshu Zhang, Quan Lu, Jianqing Gao, and Feng Ma, address the challenges of using multimodal large language models for solving geometry problems. Multimodal large language models, or MLLMs, have made impressive strides in various fields, including mathematical reasoning. However, when it comes to geometry problem solving, or GPS, these models struggle due to two main issues: a shortage of accurate, step-by-step solution data and a tendency for hallucinations, where the models generate incorrect or fabricated information during reasoning. The paper introduces a new approach called GeoGen, which is a pipeline designed to automatically generate stepwise reasoning paths for geometry diagrams. By combining precise symbolic reasoning with advanced language models, GeoGen creates large-scale, high-quality question-answer pairs. Symbolic reasoning refers to using structured, rule-based systems that apply geometry theorems logically, rather than relying on the more flexible but error-prone natural language processing of LLMs. To build on this, the researchers developed GeoLogic, a specialized large language model that's trained using the synthetic data produced by GeoGen. GeoLogic acts as a bridge between everyday natural language and these symbolic systems. This integration allows symbolic tools to verify the outputs of MLLMs, making the overall reasoning process more rigorous and helping to reduce those problematic hallucinations. Let's break down the framework they propose, as illustrated in Figure 1 of the paper. It starts with data synthesis and training. They use GeoGen to create formal data and chain-of-thought data, which are step-by-step solutions. This involves generating diagrams from public sources or through GeoGen itself, and then expanding and synthesizing the data. For instance, GeoExpand might add variations to the problems, while GeoSynth ensures the data is diverse and applicable. Once the data is ready, they perform supervised fine-tuning, or SFT, on the MLLM. This includes components like a plotter for visualizing diagrams, a target finder for identifying key elements in the problem, and the symbolic system for logical verification. They also train GeoLogic separately using this synthetic data, so it can handle the interface between language and symbols. In the inference phase, which is the actual problem-solving step, the system combines the MLLM's outputs with verification from the symbolic tools. For each geometry problem, it predicts answers and checks them against true or false validations, ensuring accuracy. The paper highlights why this matters. Existing methods for GPS often rely on chain-of-thought supervision, where models are fine-tuned on datasets that provide step-by-step reasoning in natural language. But public datasets for geometry are limited and lack high-quality examples. Some approaches try to generate more data using templates or other LLMs like GPT-4, but these have drawbacks. Templates can be too rigid and lack diversity, while LLM-generated content might still contain errors. In contrast, symbolic-based methods have proven effective for GPS because they use formal languages and theorem-proving algorithms to derive solutions systematically. However, these systems are often inflexible and require manual rule crafting, which isn't scalable. The innovation here is integrating the best of both worlds: the adaptability and language understanding of MLLMs with the precision and reliability of symbolic reasoning. Experimental results from the paper show that this combined approach significantly improves MLLM performance on geometry benchmarks. For example, by using GeoLogic to verify and refine outputs, the models achieve more accurate and interpretable results. This stems from the synergy between neural networks, which handle visual and textual inputs, and symbolic systems, which provide logical grounding. The researchers categorize their work under computing methodologies, specifically reasoning about belief and knowledge, theorem-proving algorithms, and neural networks. Key terms include geometry problem-solving, multimodal large language models, and symbolic reasoning. In the introduction, they note that GPS is a complex task involving fine-grained visual understanding, such as recognizing points, lines, and angles, and multi-step reasoning based on geometric theorems. This sets it apart from other math problems and underscores the need for specialized tools like GeoGen. Overall, this method not only addresses the data scarcity issue by generating synthetic datasets but also enhances the reliability of MLLMs through verification, paving the way for more advanced AI applications in education, automated tutoring, and beyond. The code for this project is available on GitHub for further exploration and replication.